Good day and welcome to A-Level Almini Wilson. As always, I do believe that today could be the day, and it is a perfect day to understand maths better. Okay, so let's just have that positive mindset as we dive into one of the most difficult topics in the A-Level syllabus, and that is integration. Okay, so I'm going to focus on paper 1 integration for today, so we won't be doing sine and cos and trig functions yet. We'll just do basic integration. And I do need you to have a few basic requirements ready. I need you to have a smart calculator, either this one, fx9 ZA plus 2, or the ZA plus 1 is also fine. We might need it. There is a special button you'll see that right there for integration, just to check your answer, not to take away from your own abilities. And then I would also like you to have the Cambridge formula sheet close by, because there are a few things on the formula sheet that you might use. Also, maybe just a quiet environment, stationary, and the right mindset is very important. Think that you can do this. Imagine you understanding maths better, and then you will. Hey, what you think will happen happens. So what I need you to do now is quickly just write down, I'm going to start with a basic equation, and we're just going to start by deriving it. And then once we've derived it, I'm going to show you how to integrate it, because integration is basically reverse differentiation. So if you can derive, if you've seen my video on derivatives, then you can integrate by just reversing what we've done. Okay, so first of all, notation is very important. If you have this equation and you want to derive it, you could have said dy dx, or some people prefer saying y accent, or however you want to write that down. I just want to show you then, how do we derive? The rule says times to the front, subtract 1 from the exponent. Same here, there's a little 1, times to the front, subtract 1. So technically this will be x to the power 0, and constants will fall away. Okay, so then if we need to turn this back around and we need to integrate to get back to our original curve, we will do the opposite. So have a look at my method. The method says add 1 to the top and then divide with your new exponent. Here you add 1 to the top. Now remember, there is actually x to the power 0 here. So you add 1 to the top and you divide with your new exponent. But then we have to put a plus c, because remember, if you didn't know that that was your original equation, if that was unknown in the shadows there, you wouldn't know that there was a 5. There's actually no way of knowing that there's a 5 unless they give me coordinates that I can sub in. Remember, if you have this equation, you can sub in an x and a y to get your c. You can't sub in an x and a y in this step, because technically this is gradient. Don't forget about that. That's gradient. But you can sub an x into derivative. So this is called then an independent, let me just quickly get the right wording for this, an indefinite integral, because it doesn't really have some boundaries. So we have to put the plus c. I will give you some other ways to write this down. I can, for instance, tell you to integrate by using this instruction. You see, if I did dy dx and I want to get to y, I know I have to integrate. But what if I just had like a random equation like this? This is the instruction to integrate. The integral sign and the dx tells me I need to integrate. So once you've integrated now, let's try this again. You add 1 to the top and then divide. This one just gets that, plus c. Once you've integrated, we drop this and we don't write that anymore. Also, just to prove my point from earlier, if we integrate correctly, we will get back to the original. Okay, do you see, if we integrated this, except we don't necessarily know c unless they gave us a coordinate. Okay, so this is called an indefinite integral. Let me just give you a definite integral, something with boundaries, and then we'll see how to apply boundaries. Okay, so this would have produced an indefinite integral, but now as soon as I put boundaries, let me show you where I put my boundaries. I put them there, 1 and 2. that would mean that I can apply these boundaries to my equation once it's integrated. And I'll show you how to do that. As soon as you have boundaries and you integrate, please don't put the plus c. Okay, so let's go through this slowly. You add 1 to your exponent and then divide. You add 1 to your exponent, 1, and then divide. And then what I normally do is I just put a bracket around here. You're not allowed to write this anymore. And then we just put our boundaries. And then very important, because this is a method mark, is to sub in your boundaries correctly. I'm just going to simplify. This is going to become negative x cubed. But I'm going to sub in my biggest boundary first. Always sub in your biggest boundary first, minus, and then sub in your smaller boundary. Don't make sign errors. Did you guys see my bracket usage? So it's biggest boundary minus, and then put a bracket for your smallest boundary. And then plus 21. And then you can type that into your calculator. Okay, so you just sub this all in. I get an answer of 13, but you can quickly pause the video and see if you get the same thing. Like I said, bracket usage, very important. But then I want to show you something great on the calculator. And obviously this is only once you've done the sum to check if you got it right. This button will change your life. So this is telling you I'm going to integrate. Only works if you do have boundaries. Let's type in negative 3x squared plus 20. So check negative 3, I get my x from going alpha x, negative 3x squared plus 20. Okay. Then if you want to get to your boundaries, you just move, did you see I moved my cursor? I want to use 1 and 2 as my boundaries equals. Holding thumbs, yes, we get the same. So that's how you get 13, and that's also how you use the button on your calculator. Very useful. If you made a sign error and you didn't get the same as the calculator, go back and check what went wrong. Okay, so now you might ask at this stage, what are the uses of integration? We've already discussed now if it's in derivative form. So if you're in your gradient equation like dy dx and you want to get back to the original, that's when we use integration. But something else that's also very useful is if you want to find the area under a curve. So let me just quickly give you an example. Let's say you had a nice square root graph and you wanted to find this area. That can also be obtained by integrating. There are other methods to find the area under the curve, like trapezium rule and all of that, but I'm focusing on paper 1, how to find the area under the curve. We will integrate. So let me give you an example of how we can ask something with a graph and then the area under that graph, or sometimes even the area between two graphs can get quite technical. We were speaking earlier of the square root graph. I actually want to do that one. So if that is a square root graph, actually the square root graph will look more like this, but let's focus more on like the positive quadrant of x to the power a half. I can then ask you, let me just zoom in here. Just by the way, this might be useful for you to know, but this is the positive square root graph, and this leg would be the negative square root, like y is equal to negative square root x, or x to the power of a half. When you want to find the area under that curve, I can do something like this, where I give you boundaries and I say, let's do this between 1 and 2. So now you see those boundaries that we were using earlier in the integration sign. Well, how does that apply to real life? So if I want you to find this area, let me show you how to write this down. Smallest boundary, biggest boundary, you have x to the power of a half, which is your curve, and then you want to integrate this. Okay, it's getting more difficult with square roots, right? If this was just a square root, you'd have to know that, let me just write this on the side. You have to know that square root x is x to the power of a half, step 1, because we can't really integrate when it looks like this. So then let's start the rule. Remember the rule on your formula sheet. Sorry, I hope I'm not making you nauseous, but the rule on your formula sheet actually says this. If you want to integrate this, it will become x n plus 1 over n plus 1. And remember, the formula sheet goes in with you to the exams. I can't. So this rule, if you forget how to integrate, at least it's there. Safety zone. Okay, so 2 and 1, add 1 to the exponent. and then divide. But I want to show you a trick. If this was 3/2, you can just let the bottom number flip up, and then it will become this. I promise you, okay, if you want to know why is this true, it's because if you divide by 3/2, like that, you can do like the reciprocal thing where you, instead of dividing by this, you times by the reciprocal. Tippin times, or whatever your teacher used to call it. This is much easier to do when you're working with fractions. Okay, and now I'm not technically following my own rules, because you remember what I said? As soon as you integrate, I don't want to see that anymore. So let me write this nicer. You add 1 to the top, divide, but now check my new trick. Don't write the integral anymore, and then write your boundaries. Did you notice I didn't put a plus C because we did have boundaries? That's important. All right, moving on. I do want us to sub this in now. I know it's messy, but the calculator will take care of all of this for you. Just remember, biggest boundary in first, then smaller one, and then get your answer. Okay, if you're not a fan of typing that in, you can obviously just do this. I already did this a bit earlier. I had my x to the power of a half there, my boundaries, and I got 1,21. What does this 1,21 represent? It's not an x coordinate or a y coordinate. Remember, the question was, find the area under the curve. So this is what will happen when you have your curve and you're approaching your x-axis. That is the area. Guys, while I'm busy with this sketch, I know it's not the prettiest sketch. My OCD wants me to typix that out the whole time. Let me just do it, then I'll feel better. I just didn't like that little tail hanging out there. Guys, while I'm busy with this question, I wanted to go to another level, but I need my hands for this. Okay, so what if we took that area and we spun it around the x-axis? Okay, so this is the x-axis. We will create a solid then, because you would take that whole area that you have and spin it round, almost like this is a piece of cement, and then when you take it all the way around, you're making like a pot that's full of cement. That is the next thing that we can do with integration, is we can find the volume of revolution if this area is spun around an x-axis or a y-axis. Okay, so I want to just, while we're busy with this picture, I want to introduce you to how to do volume. So far, this has been area. So also when you have the answer at the end here, you can say square units, or units squared. But when you want to do volume, I want to be close to my picture, so I'll do it right here. When you want to do the volume of revolution, say V equals, still the same boundaries, that didn't change, but there are a few things that need to be added now. You need to add a pi in front, and you also need to take whatever graph you had, if this was your curve, and you need to square it, dx. That's the formula. It's not that bad. If you remember, if you spin around the x-axis, you just remember that I need to add a pi, and you need to take whatever your y was, and then get that to be squared. I know this looks weird to say y squared, but it actually becomes an x. It's because of this. When you get your y alone, you take what y is equal to and you square it. And you square it, and then you integrate it according to the x. The reason why I'm hammering on all these variables is because sometimes they want you to spin it around the other axis. So it's important to notice that in this equation, you get y alone, you square it, and then obviously whatever that was equal to, you will integrate according to x. Okay, let's do this. This is actually much easier than the previous one because I don't have fractions. I'm just going to simplify it first. So if you take a half times 2, raising the power, I get that. Remember to drop your integration sign, integrand, when you've integrated. So let's integrate x squared over 2. You see how I did that? And then we still need to apply our boundaries, 2 and 1, but I'm sure you can do that. It's not difficult. Then just remember to add a pi at the very end. I mean, you can do your boundaries like you were doing here. And then if you want, you can just add a pi to the very front like that. And then in your answer, just let the pi chill with your answer. That is how you do volume of revolution. But I want to show you another example while we were talking about the spinning and all of that. Let's say we had an x squared equation, y is equal to x squared. We can also use the y axis. I can ask you for, let's maybe only do this part. I can ask you to get me the volume of y is equal to x squared between 0 and 1. And then what I can do is, instead of doing this, you will have to integrate then. Right. You must be careful that the y mustn't be alone then. You must make x your subject. So this is where it gets a bit tricky. Because now look at what I've done. I've got an x alone. So what I need to do also is need to make a decision. Am I using the positive or the negative? I'm using the positive x only. Remember, I gave you a domain restriction here. I said x must be bigger than 0. So the thing that you're actually going to integrate is going to be x equals square root y. You're making x the subject, and you're actually going to integrate according to y, because now I've changed everything. Let me just explain this by using my hands. I like using pointing and such. When you are approaching the x-axis, you use x boundaries and you're integrating x. But when I ask you to almost flip to your side and integrate the area approaching the y-axis, your boundaries need to be y-related, and you are integrating y. And before you can integrate y, you obviously need to make x your subject. And that's where I lose a lot of people in my class, is because x needs to be the subject. So this is now technically what I'm going to use, root y, I need to integrate. And I'm using y boundaries, so from 0 to 1. So that it needs to happen when you're approaching the y-axis. Nothing else is going to change. I'll show you. If you want to just rewrite that as a power of a half, just saving some space there, then you add 1 to the top, divide by 3/2, or just flip everything up like I did there, and then apply your boundaries, 0 and 1. That it is really as easy as that, as long as you read carefully around which axis. Am I approaching the x-axis or am I approaching the y-axis? They normally print that in bold though, I've seen on the papers, just so that even if you're in exam stress mode, you can still see, oh, x-axis, okay, or y-axis, because it does make a big difference. If you then have to do the volume of revolution spinning around this axis, you will have to just check my formula. If you do the volume of revolution around the y-axis, you go pi and then x, what x is equal to dy. And this is confusing because I know it looks like this is x, but it is actually what x is equal to. This just tells you x must be the subject, and then you must square it. So x squared in this case, you'll say what x is equal to. So x in this case was equal to root y, and then you square it. But this is the formula, hey? So when I actually do it, I know it's going to be root y, so y to the power of a half, squared dy. This dy is very important because it tells you which variable to integrate. The x is very important because it tells you who needs to be my subject. So my x needs to be my subject. I square what it is equal to, and then I integrate it. Lots of information there that had to go in. So if you want to pause, listen to that again, and then start doing some examples just to practice spinning around the x-axis, spinning around the y-axis, spinning around the x-axis. And also a while back I had a student with exam stress. Last question, they asked for, I think it was area, and he read volume. And then obviously area is easier, and then he did volume and then lost those marks, unfortunately. So please read carefully. The question will state very clearly whether it's area or volume. This person will know who he is. Anyway, let's move on. I'm happy to just quickly check with you if there's any exceptions. There can be an exception. One of the exceptions is when your area is in the negative y's. So let's just quickly do a sketch like that. Think about a nice little graph that I can sketch for you. There needs to be let me explain to you like this. If you had x squared plus x, for instance, if this is your graph, you will have two intercepts. I hope that by now you know how to get your intercepts. You make y equal to naught, then factorize. So I'm thinking the two intercepts will be -1 and 0. So it will look like this, positive parabola. Now, if I asked you to get the area between -1 and let's say 1, there is a problem because there'll be parts of it that will be below the x-axis, and then there'll be a part here that is above the x-axis. But we can't really then do it in one sum. You'll have to break it up. You'll have to say, I want the area of U, little graph. I want you between -1 and 0, so -1 and 0. Interestingly enough, if you do this on the calculator or if you do it manually, you'll get a negative area. So that's the first thing I want you to notice. If it's underneath the x-axis, it will be a negative area. You will then manually have to make it positive. Okay, and then you can then add the area of the same little graph, x squared, but now you need to be between 0 and 1, and you'll be a positive area. So just if we went through some of the steps, it'll be x3/3 plus x2/2 with your boundaries 0 and -1. 0 will obviously, let me just quickly see, it must be small to big. So I know it's confusing. Yeah, that's what was bothering me. It needs to be -1 here and 0 there. You see how quickly you can get confused with which one's bigger, because one in your head's like, one is bigger. No, 0 is bigger than -1. So your bigger boundary will be 0. You'll sub in 0 first and then -1. But I do feel like we've done that already. I don't want to waste your time. So let's just see something interesting here. If we had our equation, which was x squared plus x, and we have our boundaries -1 all the way up to 0. I am getting a -1/6. So that's great if you get -1/6. But now I said, if you want area, the only reason why this area is negative is because it's underneath the x-axis. So you need to manually make this positive, and then you add your next area. So that is quite a tricky part, knowing what to do with areas under the x-axis. Will be negative, but technically area can't be negative. It's just the placement of where the area is that's negative. So then you make it positive. Lots of information. I think can we do one more thing with area, and then I'll just quickly do chain rule, and then we're done. Then you can go sleep. I want us to discuss what happens if I'm asking you for volume or area between two graphs. Okay, so that is if you're writing headings and you're writing dates, like this is your real class, you're welcome to say area between two graphs. And then let me show you an example. So the best combination that they love asking is like some kind of parabola, and then maybe a parabola with a straight line. That's like the most common combination of two graphs. Obviously it can get more difficult, but let's just get the concept sorted. If I want the area between these two graphs, it is a little bit difficult because obviously now there are two equations to take into account, but they'll give you the two equations. Let's say this one obviously needs to have a negative gradient. So like, let's say -2x plus 7, and then the other equation will have to be a parabola, but a specific parabola, because you need to be turning, let's make it like -2 squared, because then we know that you're turning at 2. The easiest method would obviously be here to integrate the two of them. And the way that I normally do is I go integrate the top, and then I minus, and then I integrate the bottom. Very funny, my students saying this is stop and this is bottom. No, I'm saying integrate the top. Maybe I should do this. And integrate the bottom. That's how you do distance, not distance, area between two graphs. But what is of cardinal importance is to find the points of intersection first. Okay, because otherwise, if you don't have your points of intersection, you don't have your boundaries. So point of intersection, you're going to obviously set the two equal to each other. Just killing two flies with one slap, is that the expression? I'm just squaring this already, and I'm setting it equal to that one. If you then bring it over, it will be a trinomial. Don't make sign errors. and then minus 3. You can do this manually, or I haven't shown you this yet on this video. If you have a trinomial like this one and you want to factorize it, you can just go into mode 5-3 mode, which gives you an option for equation, and then you pick the trinomial option. And then you just feed in your coefficients. Coefficients 1, -2, -3. Just feed it in. 1 equals negative, now I've got short-term memory loss, -2 and -3. So when you have that, it will give you the answers. So x equals 3. So I'm just going to write here x equals 3. The other answer I'm getting is x equals -1. Okay, so x equals -1. Just put them back in your brackets. Obviously change the sign, and I'm just want to, for you, those of you that are old school, you could have done this the long way. Factors of -3 to produce -2. So it's -3 times 1 gives me -3, but if I do the FOIL, the inner outer, I get to -2x. I hope my sketch is sort of accurate. It is, hey? -3 will then be this, and 3 will be that. I'm not really interested in the y's, because I just want to show you how to set this up. We don't have to do the whole thing. You then integrate who's at the top. It'll be the straight line. So integrate the top for these specific boundaries, from -1 to 3. And then when you're done with that, dx, I do prefer you to do them separately. I'll tell you now my reasoning. Then minus, and then you integrate the bottom. Now the bottom will be this little square, and then for the same boundaries, -1 and 3. Let me just make some space. Dx, and that will give you the area between the two graphs. If you had to do this whole thing and you had to spin it around the x-axis, I do prefer you then doing it definitely separately, and then you can put a pi for that one, and you'd obviously have to get this squared then and put a pi, and then you'd have to take this whole thing squared. That would be if you had to take this and find the volume of revolution. So that is slightly different, is when you spin it to when you just have the area. That's basically everything in a nutshell about area. I just want to show you that I've got a shortcut for you if you have to do some difficult brackets. I call it reverse chain rule. So let me just quickly recap chain rule for those of you that haven't seen the derivatives video yet. If you have to derive something with a bracket, you're always welcome to times out the brackets, but sometimes it's impossible. And then we need like a backup plan. So if I give you something like 3x plus or minus 2 to the power of a half, you see that's difficult to actually times out. I hope that you're not thinking that this is equal to like 3x to the power of a half and a half minus 2 to the power of a half. I don't even want to say that. That's not right at all. So you can't times out these brackets, not with the methods that you've got at this stage. So I want to show you how to do derivative. So this is called chain rule, but it's the shortcut chain rule. If you do derive your bracket first, so if you think of the bracket as being like a physical structure, you derive the bracket, but keep the inside intact. So times to the front, subtract 1, that's derivative. Don't get confused now with derivatives and integration. Times to the front, subtract 1, and then you'll also derive the inside. So this is times by 3. So if I wrote this equation down, it would be 3 over 2, 3x minus 2 to the power of negative a half. This is my derivative. So now I want to show you how to integrate to get back to my curve. So if I had to integrate, this is called reverse chain rule or antiderivative, you add 1 to the top. So you integrate your bracket by adding 1 to the top. So this will become a half again, divide by a half, and then times by 1 over coefficient of x. Don't integrate the bracket. I've seen so many people now try and integrate the bracket. No, this is antiderivative. The 3 that you made here, you actually have to reverse there. So just notice this move, because even on the memo, sometimes this is like 2 marks and this will be a mark on its own. So very important. Let me just say the rule again. You add 1 to the top for the exponent and then divide with a new exponent times by 1 over coefficient of x. That's called reverse chain rule. And then remember, just put the plus c, because remember, we don't have boundaries or anything here. So it is important to see the plus c. If you then clean this up a little bit, the 3's can cancel, the halves will cancel. Promise you, you will get back to 3x minus 2 to the power of a half. So that is called reverse chain rule. And that's very useful when you have brackets to deal with and you have to integrate brackets. I hope that that wasn't too much information at once. I do feel like after you've watched this, it's a good idea to go do some past papers, just so that the information can go and sink into long-term memory. Thank you for joining me. I would love to keep making more videos. A video a week is what I'm aiming at. I do have constant polls on Instagram to see which topic are we going to do next. And thank you for joining me. Please subscribe.